Welcome to another episode. Before we begin, take a moment to settle in. Maybe you're lying in bed, letting your thoughts slow down. Or maybe you're somewhere quiet, where the world feels still. Wherever you are, I'm glad you're here. Tell me, in the comments, where you're listening from and what time it is there. And if you enjoy drifting through the strange and fascinating corners of science, remember to subscribe. It helps the journey continue. Now, let's talk about light. For as long as we've watched the world, light has been our truest guide. It's how we see, how we measure, how we know. It draws straight lines across space, clean and unwavering. At least, that's how it seems. In our everyday experience, light is the most obedient thing in nature. It leaves the lamp, hits the wall, reflects, refracts, but always follows a perfectly straight path through the air. And yet, there's a quiet trick hidden in that obedience. Because in the deeper fabric of the universe, light doesn't always travel straight. It bends. That sounds like a violation of its very nature. Light has no mass, no weight, nothing for gravity to grip. For centuries, physicists thought that meant it should be immune to gravity's pull. After all, gravity affects massive bodies, planets, moons, falling apples, not beams of light. But the universe had a different story in mind, one that would take us centuries to unravel. Imagine standing on a vast plain at dusk. You see the last rays of sunlight painting the sky orange. Every photon in that sunset has traveled 93 million miles, about 150 million kilometers, across empty space to reach you. For almost 8 minutes, it's been moving in what we'd call a straight line. But straight in the universe is not what it seems, because the path of that light has been gently curved, ever so slightly, by the mass of the sun itself, by the invisible geometry of space and time. Light's apparent straightness is only a local truth. On the grand scale, it flows like a river across a landscape you can't see, one sculpted by stars, planets, and galaxies. Gravity, we've come to learn, doesn't just pull on things. It reshapes the very stage on which things move. In the early 20th century, Albert Einstein gave us a language for this hidden geometry. He called it general relativity, and within its graceful equations lies a simple, astonishing idea. Matter tells space how to curve, and space tells matter how to move. Einstein once summarized it just like that. Space tells matter how to move. Matter tells space how to curve. It's a phrase that sounds almost poetic, but it redefined physics. It means that the familiar force of gravity isn't really a force at all. It's the curvature of spacetime itself. Planets orbit stars, not because they're being pulled, but because they're following the straightest possible paths through a curved universe. And light, even though it's weightless, still travels along those same paths. To light, a bent trajectory is straight because it's moving along the natural contour of the cosmic landscape. That realization didn't come easily. In Einstein's time, it was as much a philosophical leap as a scientific one. The idea that space itself could curve was almost absurd. People could imagine a planet's orbit being round, but not the space it moved through being warped. Yet the math and the logic were clear. If the sun's mass curves spacetime, then any ray of light passing near it must bend too. Not because the sun is pulling the light, but because the light is following the shortest path, a geodesic, through curved space. Einstein predicted this bending would be tiny, a deflection of just about 1.75 arc-seconds for light passing by the sun's surface. That's smaller than the width of a coin seen from 2 miles away. He didn't expect anyone to ever measure it. And yet, a few years later, someone would. But before we reach that story, the expedition that proved Einstein right and changed the way we see the universe, let's linger a bit longer on what this really means. Because it's more than physics. It's a quiet reordering of how we understand reality. The straightness of light, once the symbol of truth itself, turns out to be an illusion born from our limited perspective. We live inside a curved stage, one we can't directly feel. Every beam of light we see, every starlight glimmer that reaches our eyes, carries within it the fingerprint of gravity, a record of its long dance through the warped architecture of space. To see light as it truly moves, you must think not of lines, but of geometry, not of attraction, but of shape. Imagine space as a giant, invisible fabric. Massive objects like stars, black holes, and galaxies sink into that fabric, stretching it downward. When light passes near them, it follows the contours of the stretch, not because it wants to, but because that's the only path that exists. In everyday terms, we might picture this as a marble rolling across a stretched rubber sheet. If you drop a heavy ball on the sheet, the marble's path curves around it. It doesn't feel a force. It's simply following the sheet's shape. That's how light travels near massive objects. But of course, the real universe isn't two-dimensional rubber. It's a four-dimensional continuum, 3 dimensions of space and 1 of time, intertwined so intimately that bending one bends the other. So when light curves around a star, time itself curves with it. That's why gravitational lensing doesn't just distort what we see, it can also delay it. The universe becomes a hall of mirrors, where light from a single galaxy can take multiple paths to reach us, arriving at slightly different times. And this bending doesn't only happen near stars. Entire clusters of galaxies, each tens of millions of light-years across, can warp spacetime so much that they act like cosmic magnifying glasses, bending and focusing light from galaxies billions of light-years beyond them. Through that lensing, we can glimpse the ancient universe, magnified and multiplied by gravity's quiet artistry. Light, the very thing that reveals the universe, is also deceived by it. And yet, in that deception lies discovery. Because when light bends, it tells us something about the mass that bent it, about the shape of the cosmos, about the invisible things we can't otherwise see. Gravitational lensing is nature's own optical trick, an effect so subtle it took humanity millennia to notice. And like all great discoveries, it began with a simple act of wonder, someone asking whether even light could fall. We're going to follow that question through history, from Newton's experiments and the earliest speculations, to Einstein's revelation, to the modern telescopes mapping the universe with gravity itself as their lens. It's a story about bending, but also about seeing, and how sometimes to see the universe clearly, we first have to watch it distort. So stay with me. Close your eyes if you like. Imagine the night sky, vast, full of light traveling straight, and yet not straight at all. Somewhere out there, a photon that left a distant star 1 billion years ago is taking a long, slow curve through space, shaped by the pull of invisible giants. And that curve, imperceptible and delicate, is part of the reason we can see the universe at all. Long before Einstein curved the universe, the story of light was already tangled with mystery. To understand how we came to believe that light itself could bend, we have to return to the 17th century, a time when science was young, when the night sky was a puzzle of moving dots, and when one man with a prism and a restless mind began to see the world differently. That man, of course, was Isaac Newton. Newton lived in an age when the world was still being measured and named. Gravity was not yet a universal law. It was an intuition waiting for form. Light, meanwhile, was one of nature's strangest phenomena. It moved faster than anything else, yet no one knew what it truly was. Some believed light was made of waves, spreading like ripples through a medium they called the ether. Others thought it was composed of tiny particles, minuscule bullets racing through space. Newton, ever the geometer of nature, chose the second view. In his Optics, published in 1704, he described light as a stream of particles, corpuscles he called them, emitted from luminous bodies and traveling in straight lines until they met another medium. These corpuscles could bounce, refract, or scatter depending on the surface they struck, but they were, in Newton's imagination, physical things, infinitesimal projectiles. And that meant, in principle, that they could be influenced by gravity. Newton's universe was mechanical. Everything had a cause. If apples fell because Earth pulled on them, and if the moon stayed in orbit because gravity curved its path, then why should a particle of light be exempt from the same rule? It's easy to imagine Newton at his desk in Cambridge, candlelight flickering across pages of equations as he considered that question. He already knew that massive objects attract each other with a force that grows weaker with distance, the inverse square law. So if a corpuscle of light passed close enough to a massive body, like the sun, shouldn't its trajectory bend slightly toward it? He never worked out the full details, but the seed was planted. Even light might fall. That simple idea, gravity acting on light, was one of the earliest glimmers of gravitational lensing, centuries before the term existed. But Newton's time was a world of intuition and geometry, not precise cosmological measurement. The instruments were too crude to detect any such bending, and the speed of light itself was only roughly known. Still, Newton's influence was so vast that his way of seeing light as particles dominated scientific thought for over 100 years. Every reflection, every refraction, every rainbow was explained through the dance of corpuscles. And for a while, it worked remarkably well. But science, like light itself, doesn't always travel straight. In 1801, a German physicist named Johann Georg von Soldner took Newton's old idea seriously enough to try calculating it. Soldner was a mathematician and surveyor, a man trained to measure the curvature of Earth itself. He was also fascinated by celestial mechanics, by the way Newton's law of gravitation seemed to tie the heavens together in one grand equation. He reasoned, if light is made of particles, and if those particles move extremely fast, then the gravitational pull of a massive object like the sun should deflect their paths ever so slightly. Using Newtonian mechanics, treating light like an object moving at tremendous speed, Soldner worked out how much a ray of light grazing the sun would bend under its gravity. His answer was about 0.87 arcseconds, less than 1/1000th of a degree. To put that in perspective, that's like seeing the edge of a coin from nearly 5 kilometers away, or 3 miles, and noticing it shift by half its width. It was, for its time, a bold and delicate prediction. Unfortunately, no one could test it. To measure such a tiny shift, one would have to photograph stars near the sun's edge during a total solar eclipse, the only moment when the blinding sunlight wouldn't overwhelm the starlight behind it. In 1801, that was far beyond the reach of the technology available. So Soldner's calculation remained a curious footnote in physics, a what-if left floating in the margins of Newton's legacy. And there it stayed, quietly forgotten for more than a century. The 18th and 19th centuries brought revolutions in how we understood light itself. If Newton saw light as a stream of particles, Christian Huygens and later Thomas Young and Augustin Jean Fresnel argued that light behaved like a wave. In 1803, Young performed his famous double-slit experiment, the one that made light interfere with itself, forming bands of brightness and darkness like ripples overlapping in a pond. This wave behavior seemed incompatible with Newton's corpuscles. Light couldn't be both bullets and waves. The scientific pendulum swung firmly toward the wave theory, and with it, the notion that gravity could affect light faded into obscurity. After all, waves didn't have mass. And in the Newtonian worldview, gravity only acted on mass. So, logically, light, as a wave, should travel in perfectly straight lines through the vacuum of space, indifferent to planets and stars. Astronomers of the 19th century largely accepted this. The cosmos was imagined as a grand stage filled with radiant energy moving freely through the invisible ether, untouched by the gravitational fields that governed the dance of celestial bodies. The sun pulled planets, yes, but light. Light was thought to be untouchable. And yet, a few quiet voices kept wondering, because some phenomena refused to sit neatly within either theory. When light passed close to massive stars, strange refractions seemed to appear in the spectra. When observing double stars, pairs orbiting each other, some astronomers suspected that the path of light could be slightly distorted by one star's gravity. But the effects were too small, the instruments too blunt. So, for a time, the question slept. It would take the birth of a new physics, one that blended the mechanical and the geometric, to wake it up again. Between Newton's 17th century mechanics and Einstein's 20th century relativity stretched nearly 250 years of progress and confusion. By the late 1800s, physicists were starting to realize that Newton's tidy universe was showing cracks. James Clerk Maxwell's equations had unified electricity, magnetism, and light into a single framework, showing that light was an electromagnetic wave moving through empty space at a fixed speed, roughly 300,000 kilometers per second, or 186,000 miles per second. That discovery was dazzling, but it also raised a problem. If light's speed is fixed, relative to what? The answer, people thought, must be the ether, a subtle, invisible medium filling all of space. But experiments like Michelson and Morley's in 1887 failed to detect any trace of it. Light speed was the same in every direction, no matter how Earth moved. That made no sense under Newton's laws, but it was a clue that space and time were not as absolute as they seemed. The puzzle deepened when astronomers looked closer at Mercury, the innermost planet. Its orbit didn't quite fit Newton's predictions. The discrepancy was tiny, only 43 arcseconds per century, but persistent. Something was off in our understanding of gravity. Nature was whispering, and few were listening. And yet, for all its cracks, Newton's framework remained astonishingly powerful. His laws had predicted the existence of Neptune, guided the trajectories of comets, and explained tides and planetary motion with exquisite precision. Newton's gravity was not wrong, it was just incomplete. It treated gravity as a force acting across space, but it never explained how that force was transmitted. And it assumed light, as a particle without mass, could not feel that force in any measurable way. Still, Newton's corpuscular model left one poetic remnant that would haunt physics for generations. If light were indeed a particle, then maybe, just maybe, it could be deflected, even slightly, by the pull of a star. It was an idea ahead of its time, but missing a key ingredient, the concept of spacetime itself. Newton could describe motion within space, but not space as something that could move or bend. To him, space was the eternal, unmoving backdrop of reality. Absolute space, as he called it. Gravity acted within it, not on it. Einstein would later upend that idea entirely. He'd show that space wasn't the stage. It was part of the play. When Einstein finally published his general theory of relativity in 1915, he too calculated how much starlight should bend when passing near the sun. His answer, 1.75 arcseconds, was exactly twice what Soldner had found. The difference arose because Einstein's bending included not only the Newtonian effect of gravity acting like a pull, but also the curvature of space itself. In Newton's framework, only the motion of light through a gravitational potential mattered. In Einstein's, the entire fabric of spacetime was deformed. It's worth pausing to appreciate how extraordinary that is. Soldner, working in 1801, had managed to get halfway there, without relativity, without the concept of curved space, and without any means to test his result. He had used pure Newtonian mechanics, treating light as a tiny bullet flying close to the sun's surface, and he'd done the math correctly within that worldview. The only thing missing was the realization that the straight lines of Newton's space were not the true paths of nature. For more than a century, his paper gathered dust. Then, in 1919, after Einstein's theory made headlines, scholars dug it back up and recognized the echo, a ghost of an idea that had lived long before its time. It's easy now to think of Einstein's curved space as a natural evolution from Newton's falling apples. But the leap from one to the other was enormous. Newton's universe was simple, mechanical, and comforting. Objects had mass, forces acted at distances, and motion followed predictable paths. Einstein's universe was elastic. It bent, flexed, and folded time into space. Gravity wasn't a force anymore. It was geometry. And the moment you accept that geometry can bend, light's path must bend too. There's no way around it. But before Einstein could rewrite reality, he had to inherit the language of those who came before him, the intuitions of Newton, the forgotten calculations of Soldner, and the questions left open by centuries of observers staring up at the same stars. It's tempting to picture them all as part of one long continuum, minds connected across time, each holding a candle in the dark. Newton, watching the play of light through his prism, Soldner, scribbling equations by lamplight, and later, Einstein, sitting in a small office in Bern, imagining what it would feel like to chase a beam of light through space. All of them were, in some way, chasing the same thing: a deeper understanding of how light, the simplest of phenomena, could also be the key to the structure of everything. So by the dawn of the 20th century, the pieces were on the board. Newton had given us the laws of motion and gravity. Soldner had hinted that even light might bend. And the rest of physics had turned its gaze toward waves and fields, unaware that a revolution was coming. In just a few years, Einstein would merge all of it, space, time, gravity, and light, into a single, breathtaking vision. But before that, someone had to prove it. Not on paper, but in the sky, and that proof would arrive, quite literally, in the shadow of the sun. By the early 20th century, physics was standing on uncertain ground. Newton's laws still ruled the classroom, the telescope, and the cannon barrel, but cracks had begun to appear. Mercury's orbit refused to obey them. Light's speed ignored the motion of its source. And time itself, that steady, universal rhythm, seemed less absolute the closer scientists looked. Into this world stepped Albert Einstein, a 26-year-old patent clerk in Bern, Switzerland, who spent his evenings thinking about light. He wasn't a university professor yet, or even part of the academic establishment. He was just a quiet man with messy hair and a talent for turning impossible questions into logical thought experiments. He once said, "Imagination is more important than knowledge," and for Einstein, imagination was a laboratory with no walls. His tools were trains, clocks, and beams of light. Simple things, but rearranged in ways that reshaped the universe. He began by asking a childlike question. What would it be like to ride alongside a beam of light? If you could somehow keep up with it, you'd see the wave frozen in place, its oscillations still. But that was impossible, because the speed of light was always the same, no matter who measured it. It didn't slow down or speed up. So maybe, he thought, the problem wasn't with light. Maybe the problem was with our understanding of space and time. In 1905, his special theory of relativity shattered 2 centuries of assumptions. He showed that time and space are not fixed backgrounds, but part of a single, unified fabric, space-time. When you move fast, time slows down for you. Distances contract. Reality flexes depending on your motion. That alone was revolutionary, but it only worked for situations without gravity, a flat, uncurved universe. Einstein wasn't satisfied. The real universe, after all, is full of masses, planets, stars, galaxies, and their pull shapes everything we see. He wanted a theory that included gravity too. For the next decade, he wrestled with it, a relentless intellectual battle that consumed him. He filled notebooks with symbols, tore them apart, started over, and walked the streets of Berlin muttering equations to himself. He knew that Newton's picture of gravity, a mysterious force acting instantly across empty space, couldn't be right. No force should travel faster than light, and gravity seemed to. Something deeper had to be happening. The breakthrough came not from force, but from shape. Einstein realized that mass doesn't pull on things at a distance. Instead, mass curves the geometry of space-time itself. Imagine the universe as a vast, flexible sheet. Place a heavy ball on it. That's a star, or a planet, and the sheet dips around it. Now roll a smaller ball nearby. It doesn't move in a straight line, but in a curve, orbiting the heavier one. To the smaller ball, it feels like an invisible force is pulling it inward. But in reality, it's just following the curve of the sheet. That was Einstein's insight. Gravity is not a pull. It's the natural motion of objects through a curved space-time. It sounds simple when spoken aloud, but it required a complete reinvention of physics. To describe this curvature mathematically, Einstein used the language of geometry invented by Bernhard Riemann, a 19th-century mathematician who imagined shapes and surfaces existing in more than 3 dimensions. Riemann's geometry allowed for curvature not just on paper, but in the very structure of reality. In 1915, Einstein completed his masterpiece, the general theory of relativity. At its heart was an equation, elegant and compact, that said, in essence, space-time tells matter how to move, and matter tells space-time how to curve. He later called it the happiest thought of his life. In this vision, planets orbit stars not because they're being tugged by an invisible rope, but because they're following the straightest possible paths, called geodesics, through a curved space-time landscape. Think of geodesics as straight lines that exist within curved geometry. On Earth, the shortest path between 2 cities isn't a flat line on a map. It's a great circle around the globe. Likewise, in curved space-time, the straightest path for an object under gravity looks curved to us, because we're seeing it projected onto a flat background our minds can understand. Even light, which has no mass, follows these geodesics. It can't resist the shape of space-time any more than a marble can ignore the contours of the rubber sheet. When light passes near a massive body, its path bends, not because it's being pulled, but because space itself is warped. This was more than a theory of gravity. It was a new way of thinking about the universe itself. It unified motion, time, and geometry into one entity. In Newton's cosmos, the fabric of reality was static, an eternal stage. In Einstein's cosmos, the stage came alive. Space and time danced in response to matter and energy, stretching and curving like a living thing. And out of that dance came some of the most astonishing consequences ever predicted in science. Black holes, gravitational waves, the expansion of the universe, and, of course, the bending of light, gravitational lensing. But in 1915, those ideas were still young and untested. Einstein, ever cautious, doubted that anyone could actually measure the bending of light. He calculated that a ray passing just above the sun's surface would be deflected by about 1.75 arc-seconds, less than a tiny pinprick across the sky. At the time, even the best telescopes couldn't hope to detect such a shift under normal conditions. The sun's brightness drowned out any stars that might pass behind it. So Einstein quietly set the idea aside, thinking it might remain a mathematical curiosity, unprovable in practice. He couldn't have imagined that just 4 years later, the world would see the universe bend with its own eyes. What he could imagine, though, was the elegance of the idea itself. He once said, that when he finally derived the correct equations, he felt as though he were merely uncovering something that had always been there, as if nature herself had been waiting patiently for someone to notice. To him, beauty was a sign of truth, and his equations were beautiful. They revealed something subtle yet profound. Space and time were not separate entities. They were threads of the same cosmic fabric, woven together so tightly that stretching one inevitably distorted the other. Massive objects created dimples in that fabric, and motion through those dimples created what we call gravity. Even time ran differently depending on where you were. Near massive bodies, clocks ticked slower. Far from them, they sped up. This was no longer the clockwork universe of Newton. This was a universe made of soft geometry, elastic, relational, and deeply interconnected. A universe where the shortest path between 2 points wasn't necessarily a straight line, and where even the passage of time was part of the landscape. Einstein's contemporaries were stunned. Some didn't believe it, others couldn't even follow the mathematics. The idea that the sun could bend space itself sounded mystical, almost absurd. One physicist famously remarked, "Every man understands that light bends when it enters water, but that space itself could bend, that's too much." Einstein, however, trusted the logic. He wasn't guided by what was easy to believe, but by what was mathematically inevitable. If the universe followed his equations, light must bend. There was no alternative. In the quiet of his Berlin apartment, Einstein imagined how a beam of starlight, skimming the sun's surface, would appear to curve. He knew that during a total solar eclipse, when the sun's glare was hidden, it might be possible to see background stars near its edge appear slightly displaced, as if the sun were acting like a lens. But it was a long shot, requiring both luck and precision. He doubted anyone would ever try. And yet, others were already planning to. As his ideas spread across Europe, they reached a handful of astronomers who believed this test could be done. Among them was a quiet, bespectacled Englishman named Arthur Eddington, who would one day risk his life in the middle of a world war to prove Einstein right. But before that, Einstein had to fight another battle, not with physics, but with his own doubts. He worried he might have made a mistake. For months after publishing his theory, he checked and rechecked his calculations, sometimes losing sleep over the equations that had consumed nearly a decade of his life. But each time he returned to them, the results held. Gravity wasn't a force, it was geometry. He had turned the invisible into a shape, the intangible into a curve. In doing so, he had given humanity a new way to understand existence itself. Even today, the general theory of relativity remains one of the most precise and tested frameworks in science. Its predictions have been confirmed again and again, from the precession of Mercury to the time dilation measured by GPS satellites orbiting Earth, to the gravitational waves detected by LIGO a century later. All of them trace their origins back to Einstein's vision that the universe isn't a rigid stage, but a flexible, dynamic arena where light, matter, and time intertwine. And it all began with one small, almost unmeasurable effect, a tiny bending of light by the sun, an effect Einstein once thought no one would ever see. Soon they would, and when they did, the world would never look straight again. By 1919, the world was exhausted. The First World War had just ended. 4 years of devastation that reshaped nations, broke empires, and left millions dead. In Europe, cities were still scarred by the conflict. Railways were shattered, food was scarce, and the scientific community, once international and united by curiosity, was split by politics and grief. In that silence after the storm, a few scientists still looked upward, and one of them was a quiet English astronomer named Arthur Eddington. Eddington was known for his calm demeanor and deep faith in the power of reason. He was a Quaker, a pacifist, who had refused to fight in the war. Instead, he found peace in the sky, where the motions of the stars obeyed laws more harmonious than any written by men. And in 1919, he set out to prove something that sounded impossible, that space itself could bend. The man whose theory he wanted to test, Albert Einstein, was a German. In the aftermath of the war, that made things complicated. Germany and Britain had only just laid down their arms. To most people, the idea of an Englishman risking his career to test the theory of a German physicist would have sounded absurd, even traitorous. But Eddington didn't see nationalities. He saw truth, and he believed Einstein might be right. Einstein's general theory of relativity, published just 4 years earlier, predicted that light from distant stars passing near the Sun would be deflected by its gravity. About 1.75 arcseconds. That's an angle so small you could barely distinguish it with the naked eye if it were a single hair held at arm's length. But if someone could measure it, the implications would be enormous. It would mean Newton's gravity, the law that had guided science for over 2 centuries, was incomplete. It would mean space itself could curve. Eddington, then the director of the Cambridge Observatory, was one of the few astronomers with both the technical skill and the quiet conviction to attempt it. He had read Einstein's papers and found in them a kind of elegant inevitability. He once wrote, "The theory is beautiful beyond comparison." And beauty, to him, was not a luxury in science. It was a sign of truth. There was only one opportunity to test Einstein's prediction, during a total solar eclipse. When the moon passes directly in front of the sun, it blocks its blinding light, revealing the faint stars in the background. If starlight really bends as it grazes the sun, those stars should appear slightly shifted from their normal positions. By photographing them during the eclipse and comparing the plates to images taken months later, one could measure the deflection. It was a breathtakingly delicate experiment. The predicted shift was smaller than the thickness of a human hair on the photographic plate, and yet that fraction of a millimeter would decide whether Einstein's universe was real. 2 expeditions were organized, one led by Eddington to the island of Principe, off the west coast of Africa, and another led by Andrew Crommelin and Charles Davidson to Sobral, Brazil. Both sites were chosen because they lay along the narrow path where the eclipse of May 29, 1919, would be total. The idea was simple: redundancy. If clouds ruined one location, perhaps the other would succeed. Getting there, however, was anything but simple. Europe was still reeling from war. Transport networks were in chaos, and resources were scarce. The Royal Astronomical Society approved the plan, but the British government was hesitant to fund an expedition based on a German's theory. Eddington's Quaker status also complicated matters. He was eligible for conscription, and refusing military service could lead to prison. But his colleagues intervened, arguing that his work was of national importance. In a rare gesture of faith in science, the government exempted him from military duty on the condition that he carry out the experiment. So, in March 1919, while much of Europe tried to rebuild, Eddington packed his delicate photographic equipment, refracting telescopes, glass plates, precision mounts, and began the long journey to the tiny volcanic island of Principe. It was a humid, remote place, thick with tropical forest, known more for its cocoa plantations than for astronomy. He and his small team arrived in early May, just weeks before the eclipse. They built a temporary observatory out of timber and canvas, sweating under the equatorial heat as they assembled fragile instruments meant to capture the briefest event imaginable: a few minutes of darkness in the middle of the day. On the morning of May 29, 1919, the sky was heavy with clouds. The humidity was so dense that the air shimmered like glass. Eddington waited anxiously beside his telescope as the moon began to slide across the sun. He had only a few minutes to capture the light from distant stars passing near the sun's limb. If the clouds held, he'd have the proof Einstein needed. If not, 4 years of theory and 2 months of travel would dissolve into fog. As totality began, darkness fell over the island. The birds went silent. The temperature dropped. The sun's corona, a silver halo, blazed out across the sky. And for those few precious minutes, Eddington's telescope clicked, plate after plate, capturing what he hoped were faint star images glimmering near the sun's edge. Then, as quickly as it began, it was over. The light returned. The moon moved on. The sky, now washed in rain, closed around the team. Eddington exhaled. He wasn't sure what he had captured. Across the ocean, in Sobral, Brazil, Crommelин's team faced their own struggles. The heat there was fierce, warping the telescope mirrors and causing the images to blur. At one point, the main telescope expanded so much from the temperature change that its focus shifted mid-observation. But their backup telescope, a smaller one, worked perfectly. They too managed to photograph the stars during totality. When the plates were shipped back to England and developed, the analysis began. Eddington spent months comparing the eclipse photographs with reference images of the same star field taken when the sun was nowhere near it. The question was simple. How much had the stars' positions shifted? The results were astonishing. Eddington's data from Principe suggested a deflection of about 1.61 arcseconds. The Sobral plates showed about 1.98 arcseconds. Both were remarkably close to Einstein's prediction of 1.75 and far from the Newtonian expectation of roughly 0.87. In other words, the universe had spoken, and it sided with Einstein. On November 6, 1919, the Royal Society and the Royal Astronomical Society held a joint meeting in London to announce the findings. The room was packed, scientists, journalists, skeptics, all eager to hear whether gravity could indeed bend light. When the results were read aloud, there was a moment of stunned silence. Then came the applause. The president of the Royal Society, J. Thomson, stood up and said, "This is the most important result obtained in connection with the theory of gravitation since Newton's day." Einstein, upon hearing the news in Berlin, smiled. He reportedly told a student, "I knew the theory was correct. Whether the observations agree or not is another matter." And when a colleague later asked what he would have done if Eddington's results had disagreed, Einstein replied simply, "Then I would have felt sorry for the dear Lord." The theory is correct. The newspapers, hungry for a story of wonder after years of horror, erupted. "Revolution in science," declared the Times of London. "Newton overthrown," shouted others. The world, weary of war and disillusionment, suddenly had a new hero, a gentle, eccentric German scientist with wild hair and a mischievous smile. Einstein became an overnight celebrity. His face appeared on the front pages of newspapers across continents. He was hailed not just as a physicist, but as a philosopher, even a prophet. The idea that space could bend and that light could follow its curves captured the imagination of a public yearning for wonder. It's hard to overstate how transformative that moment was. For the first time in history, a mathematical idea about the invisible structure of reality had been confirmed by a photograph. The faint smudges of stars on Eddington's glass plates were enough to prove that space-time itself could warp and stretch, that geometry and gravity were one and the same. Yet, as with all great discoveries, controversy followed. Some astronomers questioned the precision of the measurements. The deflections were so small, the instruments so temperamental, that critics argued the results might have been influenced by bias or error. Indeed, later reanalyses of the data have shown that Eddington's uncertainties were larger than he reported. But his conclusion, that Einstein's prediction fit best, has since been confirmed countless times with far greater accuracy by radio astronomy, satellite measurements, and gravitational lensing observed by telescopes orbiting Earth. Even so, in that moment, 1919, the world didn't care about error bars or confidence intervals. It cared about meaning. After the darkest war humanity had ever endured, the universe itself seemed to whisper something transcendent, that the cosmos was not a machine of cold, unfeeling forces, but a living, curved, flexible thing, a place where even light could be persuaded to bend. Eddington, who had risked his reputation and freedom to make it possible, returned to England a quiet hero. He didn't bask in the spotlight. When reporters asked about the discovery, he spoke modestly. "It is not for me to praise Einstein's theory. It is for nature to do so." And nature, it seemed, had done exactly that. The eclipse of 1919 changed more than physics. It changed the story humanity told about itself. It united scientists who had been divided by war and reminded the world that truth, like light, can travel through the darkest shadows and still emerge, gently curved but unbroken. From that day forward, gravity would never again be seen as an invisible force pulling from afar. It would be seen for what it truly is, the quiet architecture of reality, shaping not just the motion of planets and stars, but the very path of light itself. And somewhere, in his small apartment in Berlin, Albert Einstein, the man who had doubted the world would ever prove him right, looked out his window and smiled. He had bent the universe, not with strength, but with thought. When Arthur Eddington's plates were developed in 1919, they showed more than just the displacement of starlight. They revealed a hidden grammar of the cosmos. The universe, it turned out, was fluent in geometry. Every mass, from a planet to a galaxy, speaks through the curvature of space-time, and light, obedient and weightless, listens perfectly. So how does light actually bend? What invisible hand shapes its path as it glides through the fabric of the universe? To answer that, we need to look not just at light, but at the shape of reality itself. Let's begin with a picture, the one Einstein himself used. Imagine space as a vast rubber sheet stretched tight across an endless frame. If you drop a small marble on it, it rolls straight. The surface beneath it is flat, but place something heavier on the sheet, say a bowling ball, and the surface dips around it, forming a gentle well. Now roll the marble again. Instead of a straight line, it spirals toward the depression, curving around the heavy object before escaping or falling in. That's what gravity really is. It's not a mysterious pull between objects. It's the way mass deforms the stage on which everything moves. Planets orbit stars not because they're tethered by an invisible force, but because they're following the straightest possible paths through a curved geometry. And light, which always travels straight through space, finds that straight isn't always what it seems. When a beam of light passes near a massive object, like a star, a planet, or a galaxy, the fabric of space-time is curved in such a way that the light's path itself becomes curved. To us, it looks as though gravity is bending the light. But in truth, the light is simply obeying the geometry of space. This bending can be described precisely, and though we won't write the equation here, the concept is beautifully simple. The deflection angle of light depends on two things: the mass of the object doing the bending and how close the light passes to it. The greater the mass, the deeper the curvature. The closer the light's path, the sharper the bend. You can think of it like a river winding past a mountain. From far away, the river flows straight, unaffected by the distant peak. But as it nears the mountain's base, the ground slopes and the water's path bends around it. If the mountain is enormous, say a black hole, the river could spiral inward and never emerge. That deflection angle was what Einstein calculated in 1915. A beam of light just grazing the sun would deviate by roughly 1.75 arc-seconds, the same value Eddington later confirmed. It's small because, while the sun is massive, its gravitational curvature at the surface isn't extreme. To bend light noticeably, you need immense mass or incredibly compact density, the kind found in neutron stars, black holes, and galaxy clusters. To understand why, we have to dive a little deeper into spacetime geometry. In Newton's world, gravity was a force acting at a distance, instant and invisible. But in Einstein's, mass doesn't pull. It tells space how to curve. And once curved, that space tells everything how to move. This means the shortest path between 2 points, what mathematicians call a geodesic, isn't always a straight line. On Earth, airplanes fly curved routes that look odd on a flat map but are actually the shortest paths over the globe. Similarly, in curved spacetime, light follows geodesics that look bent when seen from our flattened perspective. Now, if we imagine light as a traveler moving through this curved landscape, the gravitational potential of an object, its depth in spacetime, determines how much the traveler's path deviates. Every massive object carves out a gravitational well around itself. The deeper the well, the more light's trajectory curves. The Sun's well is relatively shallow, deep enough to hold planets, but not light. A neutron star's well is far deeper, dense enough to bend light dramatically, sometimes wrapping it nearly halfway around itself. And then, at the very edge of cosmic reason, comes the black hole, the ultimate well in spacetime. A black hole is not merely an object with strong gravity. It's a region where spacetime curves so steeply that all possible paths lead inward. Even light, the fastest traveler in the universe, cannot climb back out. Its boundary, the event horizon, marks the place where escape becomes impossible. At the heart of every black hole lies a number called the Schwarzschild radius, named after Carl Schwarzschild, who in 1916 became the first to solve Einstein's field equations for a spherical mass. This radius defines how small an object must be, for a given mass, before it becomes a black hole. If you compressed Earth to the size of a marble, about 9 millimeters across, roughly a third of an inch, it would lie within its Schwarzschild radius and become a black hole. The Sun's Schwarzschild radius is about 3 kilometers, just under 2 miles. Compress all that mass into a sphere that small, and light would forever circle within it, unable to escape. Close to such an object, space-time is so severely warped that light can loop around it multiple times before escaping, or, if it passes too close, spiral inward forever. This is where gravitational lensing becomes most dramatic. Instead of a tiny deflection, you get arcs, rings, and even full circles of light, what astronomers call Einstein rings. An Einstein ring forms when a distant light source, a massive object, and an observer all align perfectly. The light from the background source bends symmetrically around the intervening mass, forming a glowing halo. It's the universe's own optical illusion, a cosmic lens crafted by gravity itself. The math behind this is intricate, but the principle is surprisingly intuitive. The bending angle increases with the mass of the lens and decreases with the impact distance, how close the light passes to the center. So, if the same ray grazes a planet like Jupiter, the deflection is tiny, measured in micro-arc seconds. If it grazes the Sun, it's about 1.75 arc seconds. If it passes near a neutron star, it can be thousands of times greater. And near a supermassive black hole, like the one at the center of our galaxy, Sagittarius A star, which weighs about 4 million suns, light can be bent by more than 90 degrees, circling the object entirely. At that point, bending almost feels like an understatement. Space doesn't just curve, it folds in on itself. Astronomers have even used these extreme bends to visualize the unseeable. When the Event Horizon Telescope captured the first image of a black hole's shadow in 2019, what we saw wasn't the black hole itself. It was light, warped into a glowing ring by the surrounding spacetime. Every photon in that image had traveled around a gravitational well so deep that it bent back toward us, forming a halo of fire around darkness. A photograph of geometry itself. On smaller scales, the same principle lets us weigh the invisible. By studying how much light bends around galaxies and clusters, astronomers can calculate their total mass, even the part that doesn't emit light at all. That's how we know dark matter exists. It reveals itself not by shining, but by bending light. Everywhere we look, from the sun's gentle curve to the violent spirals near black holes, the rule is the same. Mass shapes space, and space shapes motion. Even photons, those massless messengers, cannot ignore the architecture of the universe. But bending light isn't just about distortion, it's also about magnification. Gravity can act as a lens, amplifying light from distant galaxies and quasars far beyond the reach of our telescopes. These cosmic lenses have become some of the most powerful tools in modern astronomy, letting us peer deeper into space and further back in time than ever before. In a sense, every act of lensing is a story of time itself. Light from a distant galaxy may take billions of years to reach us. Along the way, it weaves through warped valleys of space-time, its path lengthened and twisted by gravity's hand. When it finally arrives, we see not just where the source is, but where it was, often multiple versions of it, separated by time delays. Some of those images show events that happened years, decades, or centuries apart, all superimposed in the same view. It's humbling to realize that even the light we see now may have taken a detour, a cosmic, scenic route dictated by invisible mass. The night sky is not a flat map, it's a living lens. All of this stems from that single, simple insight Einstein had over a century ago, that what we call gravity is really the curvature of space-time, and that even light, the symbol of straightness, must bow to geometry. It's almost poetic. The universe bends the thing that lets us see it. Light may travel at the fastest speed possible, but it cannot travel wherever it wants. The cosmos decides its path, one curve at a time, and somewhere in that curved path lies the reason we can see galaxies that should be invisible, measure dark matter that refuses to glow, and even glimpse the silhouette of black holes against their own warped light. In the end, the bending of light is not a trick, it's a translation. It tells us that space and time are not empty. They are elastic, dynamic, and alive. And every beam of starlight on its long journey through that cosmic fabric carries the signature of the masses it has passed, a quiet record of every curve it ever took. When you look up tonight and see a star, remember, you're not seeing it where it is, but where it was. Its light curved and delayed by the very shape of the universe. You are, in a sense, gazing through gravity's own lens, a masterpiece sculpted from space itself. By the time Einstein's theory began to ripple through the world of astronomy, light itself had become something new, not just illumination, but information. Every photon, every flicker of starlight carried a story written in the geometry of space. And as telescopes grew sharper and the skies darker, humanity began to read those stories. What we found was astonishing. The universe isn't just filled with light, it's full of lenses. Every massive object, a star, a planet, a cluster of galaxies, can bend and focus light. Some lenses twist space so dramatically that they paint arcs and circles across the sky. Others are so subtle that they distort the shapes of galaxies by less than 1%. And sometimes, a single star magnifies another for just a fleeting moment, a cosmic alignment gone as quickly as it appears. These are the three great forms of gravitational lensing: strong, weak, and microlensing. Different in scale, but all governed by the same quiet rule: light follows where space curves. Imagine looking into a cosmic mirror that doesn't just reflect, but reshapes reality. That's strong gravitational lensing, the most dramatic form, where gravity acts like a powerful magnifying glass, splitting one object into many. It happens when an enormous mass, like a cluster of galaxies, sits directly between us and a distant light source. The cluster's combined gravity bends spacetime so steeply that light from the background object can reach us along multiple paths. We see several images of the same galaxy, sometimes arranged in arcs, sometimes in perfect symmetry around the lens. One of the most famous examples is the Einstein cross, a cosmic masterpiece that looks almost too deliberate to be natural. At its center lies a galaxy about 400 million light-years away. Behind it, much farther out, some 8 billion light-years distant, shines a quasar, a blazing core of a young galaxy powered by a supermassive black hole. The gravity of the nearer galaxy bends the quasar's light into 4 distinct images, forming a near-perfect cross around the galactic core. From Earth, it looks like a celestial emblem, 4 points of light suspended symmetrically in space. The first photographs of the Einstein cross in the 1980s stunned astronomers. It wasn't an artist's illusion or an artifact of the telescope. It was real. Einstein's equations, scribbled in 1915, had predicted this very thing decades before. He had even joked once that we'd never see such a phenomenon since the chances of perfect alignment are so small. Yet the universe, ever generous with its improbabilities, proved him wrong. Strong lensing creates more than just multiple images. Sometimes it stretches entire galaxies into graceful arcs or complete circles, Einstein rings, when the alignment between source, lens, and observer is nearly perfect. These rings are not rare. They appear in many deep space photographs, glowing like cosmic jewelry. Each one is a time machine, showing the same distant object from slightly different paths and moments in time. One particularly striking example is the cosmic horseshoe, discovered in 2007, a near-complete ring of blue light, 10 billion light-years away, wrapped around a massive red galaxy that acts as the lens. The effect is so precise that astronomers can use it to measure the distribution of both visible and invisible matter within the lensing galaxy. Strong lensing has become a cosmic laboratory. By studying how light is deflected, scientists can map mass, not just the glowing stars, but the dark matter surrounding them. Clusters like Abell 1689 and Max J 1149 plus 2223 act as natural telescopes, magnifying distant galaxies that would otherwise be invisible, letting us peer back to a time when the universe was only a few 100 million years old. When you see those luminous arcs in Hubble images, you're not looking at galaxies as they appear. You're looking at them through the universe's own optical machinery, stretched and repeated by the gravity of giants. If strong lensing is cosmic drama, weak lensing is its whisper. There are no multiple images, no dazzling arcs or rings, only the faintest distortions, detectable only through careful statistics. Yet it's in these quiet warps that some of the universe's most profound secrets are hidden. Weak lensing occurs when light from distant galaxies passes through large-scale structures, vast webs of matter, both luminous and dark, on its way to Earth. The deflections are small, but not random. Over millions of galaxies, the average pattern reveals a map of how matter, especially dark matter, is distributed across the universe. To the naked eye, the distortions are imperceptible. But when astronomers analyze thousands of galaxy images, they find that their shapes aren't truly random. They're slightly stretched in consistent directions, like reflections on a rippling pond. This collective distortion, called shear, is the signature of weak lensing. The beauty of it lies in its reach. Strong lensing shows us individual, rare alignments. Weak lensing, on the other hand, reveals the grand architecture of the cosmos. It allows astronomers to map the cosmic web, the vast network of filaments and clusters formed by dark matter's gravity. One of the most famous cases is the Bullet Cluster, a pair of galaxy clusters that collided roughly 3.8 billion light-years away. When astronomers observed it, they found something extraordinary. The hot gas, which makes up most of the visible matter, had slowed down during the collision and now sat between the two clusters. But weak lensing maps, which reveal where most of the mass actually is, showed that the gravitational centers were not in the gas. They were in two separate regions that had passed through each other, almost unaffected. Those invisible regions contained the majority of the cluster's mass, and yet emitted no light. It was the most direct evidence ever found for dark matter, unseen substance that makes up about 85% of the universe's matter content. Weak lensing has since become one of the main tools for studying dark matter and dark energy. Modern surveys like the Dark Energy Survey in Chile and the Hypersuprime CAM project in Japan use it to map the subtle distortions of billions of galaxies. By doing so, they can measure how cosmic structures grow over time. A fingerprint of the universe's expansion and the mysterious energy accelerating it. It's almost poetic that we study what cannot be seen by watching how it bends what can. The faint shimmer of galaxies across the night sky is enough to reveal the shape of the invisible, like watching wind by the way it ripples through grass. If strong lensing is a spectacle and weak lensing a whisper, microlensing is a blink, a fleeting alignment that lasts only days or weeks. It happens when a single star or even a planet passes directly in front of another star from our point of view. The gravity of the foreground object bends the background star's light, focusing it like a magnifying glass. The result is a temporary brightening. The star appears to flare, then fade, with no other sign of change. Unlike strong and weak lensing, microlensing doesn't produce multiple images because the separation between them is far too small to resolve. Instead, all the light blends together, causing a smooth, symmetric increase in brightness. Microlensing was first proposed in the 1930s by Albert Einstein himself, though he doubted it would ever be observed. In a letter, he called it of little practical use. Once again, he underestimated both the universe's generosity and human persistence. By the late 20th century, astronomers had the tools to detect it. Surveys like OGLE, Optical Gravitational Lensing Experiment in Poland, and MACHO, Massive Compact Halo Objects in Australia, began monitoring millions of stars in the Milky Way, looking for these telltale flickers. And they found them. One of the earliest detections came from a brightening event in the Large Magellanic Cloud, a nearby dwarf galaxy about 160,000 light-years away. The light curve, the star's changing brightness over time, matched perfectly the pattern predicted by microlensing. No explosion, no variable star, just gravity doing what gravity does best, bending space and amplifying light. But microlensing soon revealed something even more astonishing. It could find planets. When a star with an orbiting planet passes in front of a more distant star, the planet's smaller gravitational field adds a brief, extra bump to the light curve, a tiny flicker within the main brightening event. By studying these flickers, astronomers have discovered exoplanets thousands of light-years away, worlds we could never detect by any other method. Some of them orbit faint, cold stars. Some drift freely through space, unattached to any sun. We call them rogue planets, wandering worlds adrift in darkness, found only because their gravity bent light for a fleeting instant. Microlensing has even helped estimate how many planets might populate the Milky Way. The answer is staggering, more planets than stars. Some studies suggest there could be tens of billions of free-floating planets, invisible to telescopes yet revealed by these momentary gravitational alignments. In a way, microlensing is like eavesdropping on the universe, catching brief, coincidental moments when celestial bodies line up just right. They never happen again in exactly the same way, but each one adds to the story of how gravity connects everything. Together, these three forms of lensing, strong, weak, and micro, form a continuum of cosmic insight. From the colossal arcs around galaxies to the faint shears in the fabric of the cosmic web, down to the single flicker of a distant star, all are expressions of the same truth. Gravity bends light, and light reveals gravity. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. And nowhere is that truer than in gravitational lensing, where beauty and precision meet, and where the universe, through the gentle curvature of spacetime, allows us to see both its hidden mass and its ancient past. When you look at those deep space photographs, the arcs, the rings, the subtle smudges, remember that you are seeing light's long journey made visible by geometry. Every distortion is a fingerprint of mass. Every arc is a signature of spacetime's curvature. Every brightening, a whisper from gravity's lens. It's not just light being bent. It's our understanding, curved ever closer to the truth. Gravitational lensing doesn't just bend light. It gives us a window into the unreachable. Across billions of light years, the universe acts as its own telescope, using gravity as the glass. What Einstein once described as a tiny, almost unobservable quirk of nature has become one of astronomy's most powerful tools, a way to see the invisible and measure the immeasurable. When light from a distant galaxy begins its journey, it travels through a cosmic landscape filled with mass, stars, clusters, filaments of dark matter. Each one curves space just a little, and those curves, when aligned in the right way, magnify the light. If you could trace that photon's path, it wouldn't look like a straight line, but a series of graceful detours, a route shaped by every gravity well it encountered on the way. To the astronomer's eye, those distortions are a gift. They take galaxies so far away that their light would otherwise be lost in the darkness, and they stretch them, brighten them, and sometimes multiply them across the sky. Massive galaxy clusters, collections of hundreds or thousands of galaxies bound together, are especially good at this. They're like giant optical lenses, bending light from galaxies far behind them, focusing it toward us. In a sense, these clusters are nature's observatories, cosmic magnifying glasses scattered across space. Their gravity can amplify the light of background objects by factors of 10, 100, or even more. Without them, the early universe would remain hidden, its first galaxies forever out of reach. One of the earliest and most striking examples came from the Hubble Space Telescope in the 1990s. Hubble began taking deep-field images, long exposures pointed at seemingly empty patches of sky. What appeared blank to the human eye revealed thousands of galaxies, each one a system of stars billions of light-years away. And among them were strange, curved smears of light, the signatures of gravitational lensing. Astronomers realized that Hubble wasn't just photographing galaxies, it was looking through them. Massive foreground clusters were bending and magnifying the light of galaxies behind them, turning Hubble's 2.4-meter mirror into something far more powerful. In 2014, NASA launched the Frontier Fields program, deliberately using these cosmic lenses to peer deeper into the past than ever before. 6 massive clusters, including Able 2744, nicknamed Pandora's Cluster, and MaxJ 0416.1-2403, became natural telescopes. Hubble's images of these regions revealed galaxies that existed when the universe was less than 1 billion years old. Their light had traveled for over 13 billion years, longer than Earth has existed, yet it still reached us, magnified by the gravity of intervening clusters. It's an astonishing idea. We're seeing the faintest, most ancient structures in the universe, not by building bigger telescopes, but by letting the universe lend us its own. When the James Webb Space Telescope, JWST, began observing in 2022, gravitational lensing became even more transformative. With its enormous mirror and infrared vision, Webb could see the stretched, reddened light of the earliest galaxies with unparalleled clarity. In some of its first images, like those from the SMACS0723 cluster, the effect was dazzling. Distant galaxies warped into arcs and spirals, their light amplified dozens of times by the cluster's immense gravity. Some of these galaxies, discovered through lensing, are the oldest ever seen, dating to just a few 100 million years after the Big Bang. They show us the first generations of stars, the building blocks of everything that would follow. Without gravitational lensing, we might never have known they existed. In these images, time and space intertwine. Each curved streak is a snapshot from the deep past, light that left its home before the Milky Way was even formed. In some cases, lensing produces multiple images of the same galaxy, each taking a slightly different route through spacetime to reach us. Those paths are not equal. Some are longer, some shorter, so the images arrive at different times. We can literally see the same event from different moments in cosmic history, separated by years or even decades of delay. This time delay is more than poetic, it's measurable. By comparing how long light takes along different lensing paths, astronomers can determine how fast the universe is expanding. This is one of the most precise methods for calculating the Hubble constant, the rate at which galaxies recede from each other as the cosmos grows. Each lens acts as a kind of stopwatch written in gravity, marking the rhythm of the universe itself. Gravitational lensing, then, is both telescope and ruler, a tool for seeing farther and for measuring the very fabric of spacetime. It bridges the smallest scales, where microlensing finds hidden planets, with the largest, where entire clusters map out the cosmic web. When astronomers look at the warped arcs in a Hubble or JWST image, they don't just see distortion. They see depth, layers of space and time folded together, telling us about the unseen scaffolding of the cosmos. The visible galaxies are just the tip of the iceberg. Behind them lies a vast sea of dark matter, shaping the light's every curve. It's almost ironic. To understand the early universe, to glimpse the first sparks of creation, we rely on one of its most powerful distortions. We don't look straight at the truth. We see it bent, magnified, and multiplied by gravity's lens. And yet, in that bending, we find clarity. When you see those breathtaking JWST images filled with glowing arcs and distant galaxies, you're not looking at a simple photograph. You're looking through billions of years of space-time curvature, the light of ancient stars focused and sent to us by the invisible hands of gravity. The universe is not just a spectacle, it's an instrument, one that builds its own optics. And through those natural magnifying glasses scattered across the cosmos, we're not only seeing farther than ever before, we're watching creation itself, magnified through the gentle curve of space-time. The universe is full of ghosts, not the kind that haunt old houses, but the kind that hold galaxies together. We call them dark matter, and though we can't see or touch them, their presence is undeniable. They outweigh all the stars, planets, and gas we know by nearly 6 to 1. And yet, they emit no light, reflect no light, absorb no light. They're invisible, revealed only by the way they bend gravity itself. Gravitational lensing turned out to be the universe's confession, the way the cosmos accidentally lets us glimpse its hidden architecture. For decades, astronomers suspected something unseen was shaping galaxies, but they couldn't prove it. Lensing changed that. It made the invisible visible. The first clues came not from lenses, but from rotation. In the 1970s, American astronomer Vera Rubin began measuring how stars orbit within spiral galaxies. If you picture a galaxy like the Milky Way, it spins. The inner stars circle the center faster than the outer ones, just as planets orbit the sun. According to Newton's laws, the farther a star is from the center, the slower it should move, because the gravitational pull weakens with distance. But when Rubin and her collaborator Kent Ford measured those speeds, they found something that defied every expectation. The outer stars weren't slowing down. They were moving just as fast as the inner ones, sometimes even faster. That made no sense. There wasn't enough visible mass to keep them bound. By all logic, the galaxies should have torn themselves apart. The only explanation was that most of the mass was missing, an unseen halo of matter surrounding every galaxy, extending far beyond the luminous disk. Rubin's rotation curves, flat, steady lines where the speeds should have dropped, became the first clear fingerprints of dark matter. At first, many dismissed the idea. Maybe the data were wrong, or maybe Newton's gravity didn't hold on galactic scales. But then gravitational lensing came along, and it drew the same conclusion with light itself as witness. Einstein's theory told us that light bends in response to mass, not just visible mass, but all mass. That meant if you mapped how background galaxies were distorted by foreground ones, you could infer where the mass really was, even if it didn't glow. And when astronomers began doing that, the maps didn't match what the telescopes showed. They revealed far more mass than starlight could explain. Everywhere they looked, in galaxies, clusters, even vast cosmic webs, there was invisible weight sculpting space-time. The lensing didn't lie. The most dramatic example came in 2006 with the discovery of the Bullet Cluster, a cosmic collision frozen in light. Two massive galaxy clusters had slammed into each other billions of years ago, passing through one another like slow-motion bullets. When astronomers observed the aftermath, they used X-ray telescopes to see the hot gas, the luminous matter that makes up most of the normal mass in clusters. It glowed beautifully in pink and purple, stretched and shocked by the collision. Then they used gravitational lensing to map the true distribution of mass, by observing how the background galaxies were distorted by the cluster's gravity. The lensing map, shown in blue, didn't line up with the gas. It followed the galaxies, not the visible matter, but the invisible halos of dark matter that had sailed through the collision almost unaffected. The hot gas, made of protons and electrons, had collided and slowed down. But dark matter, which doesn't interact with itself or with normal matter except through gravity, passed straight through. The separation between the gas and the gravitational lensing signal was undeniable. For the first time, we could see dark matter's ghostly fingerprint across millions of light years. The Bullet Cluster became the smoking gun, the clearest evidence that dark matter wasn't just a mathematical trick, but a real physical substance. Its behavior fit perfectly with Einstein's curved spacetime. The lensing showed where gravity was, not where light was. Since then, similar observations have piled up. Able 520, Max J 0025.4-1222, and the El Gordo cluster, all telling the same story. Whenever clusters collide, the invisible mass always separates from the glowing gas. It's like watching two invisible ghosts walk through a fog and seeing the mist swirl behind them. Today, gravitational lensing has become one of the strongest tools for studying dark matter's distribution. Weak lensing surveys, like the Dark Energy Survey in Euclid, measure subtle distortions in billions of galaxies to map the cosmic web, an immense network of filaments where dark matter gathers and galaxies form like dew on its threads. The patterns of lensing tell us not only where dark matter is, but how it shapes the universe's structure. In a way, every gravitational lens is an X-ray of the cosmos, revealing the skeleton beneath the light. The galaxies we see, the bright swirling disks of stars, are just the visible tips of enormous dark halos that dominate their gravity. The true form of a galaxy isn't what telescopes show, but what its lensing reveals. Rubin once said, "We have peered into a new world and have seen that it is more mysterious and more wonderful than we imagined." Her words fit perfectly with lensing's revelation. By following the paths of bent light, we've uncovered the hidden scaffolding of the universe. What makes this so haunting is how quiet dark matter is. It doesn't collide, burn, or shine. It doesn't announce itself with heat or radiation. It simply shapes and lets the light tell its story. The stars move to its rhythm. The galaxies spin within its halos. And when light from the distant universe passes through, dark matter warps it, magnifies it, and whispers to us through those distortions, "I am here." In the end, gravitational lensing did more than confirm Einstein's theory. It revealed the missing half of creation. It showed that the universe we see is only a faint shimmer on the surface of something deeper and unseen. A hidden realm that binds galaxies, bends light, and holds the cosmos together. And the irony is beautiful. We found the darkest matter in the universe, not by looking for it directly, but by watching how it bends the light. The universe, in its own way, illuminated its own shadow. If you could peel back all the galaxies, all the stars, and all the clouds of gas, if you could see to the edge of time, the universe would glow faintly with the afterlight of its own beginning. That glow still fills the cosmos today. It's not bright like starlight or colorful like nebulae. It's a uniform, gentle radiation that comes from every direction, like a whisper from the past. We call it the cosmic microwave background, or CMB, the oldest light we can see. It was born about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral atoms. Before that, space was an opaque plasma. Light couldn't travel freely. But once atoms formed, the fog lifted, and the first photons began their journey through space. Those same photons are still traveling, reaching us now after 13.8 billion years of cosmic wandering. To the early observers who first detected the CMB in 1965, Arno Penzias and Robert Wilson, accidentally hearing it as radio noise in their antenna, it seemed perfectly uniform. But later missions like COBE, WMAP, and Planck revealed tiny variations in its temperature, hot and cold spots just millionths of a degree apart. Those tiny fluctuations are the fingerprints of the early universe, the seeds from which all galaxies, stars, and planets would eventually grow. At first glance, the CMB looks like a random static pattern, but there's hidden order in it. Every ripple encodes information about the universe's contents and its geometry. And one of the most powerful tools for decoding it is gravitational lensing. Even though the CMB is ancient, the light we see today hasn't traveled in a straight line since it left that primordial plasma. On its 13.8 billion year journey, it's passed through the entire history of cosmic structure, clusters of galaxies, filaments of dark matter, and enormous voids. Each of those masses has gently bent and distorted the light, warping the original pattern of the CMB just slightly. The effect is minuscule, but it's there. Wherever space-time curves, the CMB's faint texture twists with it. The once pristine pattern becomes subtly smudged, like a reflection rippled by waves. By measuring those distortions, scientists can map the total distribution of matter, both visible and dark, throughout the universe. This is gravitational lensing of the CMB, and it turns the entire cosmos into one vast experiment in geometry. The idea is elegant. If the universe were perfectly smooth and flat, the CMB would look perfectly Gaussian, its fluctuations random and symmetric. But lensing introduces correlations, linking far apart regions of the sky, subtly stretching and magnifying the patterns. From those distortions, we can reconstruct the invisible landscape the light passed through, a three-dimensional map of matter across cosmic time. The Planck satellite, launched by the European Space Agency in 2009, measured the CMB with exquisite precision. It didn't just map the temperature variations, It detected how those variations were lensed. The results were astonishingly detailed, a full sky map showing how mass, both luminous and dark, is distributed across the universe. It was like tracing the fingerprint of gravity itself over the face of the early cosmos. From Planck's data, cosmologists could infer not just where matter was, but how much of it there is. They could measure the proportions of ordinary matter, and dark energy that shape the universe's evolution. The CMB lensing data confirmed a picture both strange and elegant. About 5% normal matter, 27% dark matter, and 68% dark energy, the mysterious force driving cosmic expansion. And this was not guesswork. It was geometry written in ancient light. More recently, experiments like the Atacama Cosmology Telescope, ACT, in Chile and the South Pole Telescope, SPT, have refined this technique further. Unlike Planck, which surveyed the whole sky, these ground-based telescopes focus on smaller patches with even higher resolution, detecting faint polarization patterns in the CMB, tiny directional signatures caused by lensing. Those patterns let astronomers trace how structures grew over time, connecting the smooth early universe to the clumpy, galaxy-filled cosmos we see today. Each new dataset sharpens our picture. ACAT's 2023 results, for instance, provided one of the clearest lensing maps ever made, revealing, with breathtaking accuracy, the cosmic scaffolding from just a few 100,000 years after the Big Bang to the present. It's as if we've taken an X-ray of the universe's skeleton and watched how it expanded, cooled, and settled into its current shape. Through these measurements, gravitational lensing has become a kind of cosmic ruler. It helps constrain key cosmological parameters, the Hubble constant, which describes the universe's expansion rate, the matter density parameter, which tells us how much mass fills space, and the curvature parameter, which reveals the universe's shape. And so far, the results point to something remarkable. On large scales, the universe appears to be flat. Not curved like a sphere or a saddle, but balanced on the knife edge of geometry, a spacetime that extends evenly in all directions, yet expands faster and faster with time. That flatness, confirmed by CMB lensing, is one of the great triumphs of modern cosmology. It supports the inflationary theory, the idea that the universe expanded exponentially fast in its first instant, ironing out any wrinkles in its geometry. But perhaps even more fascinating is what CMB lensing tells us about evolution. By comparing lensing maps at different cosmic epochs, astronomers can see how matter clustered under gravity, how dark energy slowed or accelerated that growth, and whether the fundamental laws of physics have changed over billions of years. So far, they haven't. Gravity, it seems, has behaved consistently since the beginning, the same elegant curvature Einstein described over a century ago. It's astonishing to think that photons born when the universe was still glowing plasma now carry the record of everything that happened between then and now. Each one has traveled through eons of expansion, through webs of dark matter, and around galaxies that didn't even exist when it set out. And now, as those photons finally reach our telescopes, they tell us about every invisible mass they ever passed. In that sense, the cosmic microwave background isn't just ancient light. It's a message, a hologram of gravity. Its faint ripples and warps are the universe remembering its own formation, written in light and curvature. When you see a CMB map, that speckled oval of reds and blues, you're looking at a baby picture of the cosmos, one gently distorted by the gravity of everything that ever existed. Every pixel is a story of space-time bending and light obeying, of geometry sculpted by mass, of a universe that has been curving since the moment it began. And we, standing here billions of years later, are simply the first creatures to read it. Among all the places where light can wander, none are stranger than the edge of a black hole. It's the ultimate test of Einstein's geometry, where space-time folds so tightly that the rules of intuition collapse. Here, gravity doesn't just bend light, it traps it, whirls it, and sometimes lets it circle endlessly before deciding whether to release it or devour it. To understand this place, imagine the fabric of space as a deep well. A planet like Earth makes a small dent in that well. The Sun makes a much deeper one. But a black hole, that's a puncture, a place where the fabric doesn't just dip, it drops away entirely. It's a region where space and time trade roles, where the direction forward becomes inward, and all paths lead to a single destination: the singularity. At the boundary of this abyss lies the event horizon, the ultimate point of no return. Anything that crosses it, even light, is gone forever from our universe. But just outside that boundary, at about 1.5 times the Schwarzschild radius, lies something extraordinary: the photon sphere. The photon sphere is a ring-shaped region where gravity is so strong that light can orbit the black hole in perfect circles. If you could stand there, though stand is a meaningless word in such a place, you'd see the back of your own head as your own light completed a loop around the hole. Of course, nothing could actually survive there. Time itself stretches infinitely thin. But the idea is real, and it's part of what makes black holes the most powerful natural lenses in existence. When light passes near a black hole, it doesn't simply curve, it can wrap around multiple times before escaping. A single star behind a black hole could appear as several copies of itself, arranged in concentric rings. These repeating images are called relativistic images, and while they're far too faint for current telescopes to see, the physics predicts them perfectly. Black holes, in this sense, are not just destroyers, they're artists, sculpting light into patterns of infinite recursion. The space around them glows, not from the hole itself, but from the accretion disk, a swirling storm of gas, dust, and plasma spiraling inward. As material falls toward the event horizon, it compresses and heats to millions of degrees, emitting intense radiation. Magnetic fields twist through it, and shock waves ripple like thunder through its fiery whirlpool. This is the last dance of matter before oblivion, chaotic, luminous, and beautiful. The bending of light near this inferno is extreme. Photons emitted from the far side of the disk can loop around the black hole and emerge toward us, allowing us to see both the front and the back of the disk at once. That's why images of black holes often look like glowing rings, not because the disk is circular from every angle, but because gravity folds its light into view. We're seeing light that should have been lost, resurrected by curvature. In 2019, humanity saw this effect directly for the first time. After years of preparation, a network of radio telescopes across the globe, from Hawaii to the South Pole, combined their signals to create a virtual telescope the size of Earth itself. It was called the Event Horizon Telescope, EHT. Its target, a supermassive black hole at the heart of the galaxy M87 55 million light-years away. The result became one of the most iconic images in the history of science, a glowing, lopsided ring surrounding a dark center. That dark center wasn't the black hole itself, but its shadow, the region where light falls inward and never returns. The ring around it was the hot accretion disk, warped by gravity until its far side curved into view. It was, quite literally, a photograph of space-time bending, and it looked exactly as Einstein's equations had foretold. The brightness asymmetry, one side glowing more than the other, wasn't artistic interpretation. It came from relativistic beaming, the effect of light being boosted in brightness as the disk's rotation flung material toward us at a significant fraction of the speed of light. The image was the universe performing relativity in plain sight. A few years later, in 2022, the same technique gave us a second glimpse. the black hole at the center of our own galaxy, Sagittarius A star. Smaller, fainter, and far more turbulent than M87 star, it still produced the same ethereal halo, a glowing ring of bent light marking the horizon between what can and cannot escape. For a moment, humanity stared into the geometry of nothingness and saw something impossibly real. But long before that image existed, one movie had already brought this vision to life on screen. In 2014, director Christopher Nolan's Interstellar featured a black hole named Gargantua, rendered with haunting realism. Its swirling light, distorted into a glowing ring above and below the hole, wasn't a special effects fantasy. It was based on real physics. Physicist Kip Thorne, a Nobel laureate and one of the world's leading experts on general relativity, worked with visual artists to ensure the simulation obeyed Einstein's equations exactly. Thorne's team built a custom rendering engine that traced how every beam of light would move near a spinning black hole, accounting for the photon sphere, frame dragging, and gravitational redshift. The result was stunning, a luminous disk that wrapped itself over the top of the black hole, its light sheared and stretched into surreal beauty. Audiences thought it was science fiction. In truth, it was the most accurate visual representation of a black hole ever created, until EHT's real image confirmed it 5 years later. The scene where the crew of the Endurance approaches Gargantua captures something deeply true about the physics. Time itself slows near such gravity. For them, an hour near the black hole's horizon costs 7 years on Earth. That isn't poetic exaggeration, it's relativity in action. The deeper you are in a gravitational well, the slower your clock ticks. The same effect makes GPS satellites need constant corrections, though the difference is only billionths of a second. Near Gargantua, the difference becomes destiny. The way Interstellar blended theory and imagination echoes a broader truth. Gravitational lensing is where physics becomes art. It shows us that light, the purest symbol of straightness, can be folded into rings, spirals, and halos by the curvature of space-time. It reminds us that what we see depends entirely on where we stand, and that even the darkest places in the universe can shine through distortion. When we look at the image of M87 star, or the shimmering visualization of Gargantua, we're seeing the same phenomenon that Einstein predicted over a century ago. Light tracing the contours of curved space, painting its path around gravity's abyss. In the silence beyond words, a black hole is both mirror and mystery. It reflects our understanding back at us, warped, delayed, magnified, and in doing so, it shows us how far the mind can travel when it dares to follow light into the dark. When you look up at the night sky, it feels like a simple act, a glance into the quiet vastness above. But it isn't simple at all. Every star you see, every faint smudge of light, is a lie told beautifully. We are not seeing where things are, only where they were. And even that version of them has been gently bent, delayed, and rearranged by the invisible architecture of space-time. The photons that reach your eyes tonight may have left their source thousands, millions, or even billions of years ago. They've crossed cosmic valleys and mountains of gravity, weaving around galaxies, slipping past clusters, their paths deflected by the unseen hand of mass. By the time they arrive, the source may be gone, burned out, collapsed, or swallowed by a black hole. Yet its light still speaks, telling a story that ended long ago. It means that when we look into the sky, we're not observing the present universe, but its memory, a gallery of light shaped by time. Even the constellations we know so well are illusions stitched together from different centuries of starlight. Orion's belt, for example, is a patchwork of stars that would appear scattered and meaningless if seen from another point in space. Our familiar sky exists only from here, now, through this peculiar curvature of light and perspective. It's strange, then, that our entire sense of truth and direction rests on something so deceptive. We speak of straight lines, of seeing clearly, as if those were simple, objective things. But in a curved universe, straightness itself is subjective. A local illusion. Light always travels in the straightest possible line, but only within its own geometry. If space is curved, that straight line bends. The universe, it seems, has a fondness for irony. Even the universe, we might say, has a taste for optical illusions. It bends the thing we trust most, light, just enough to remind us that nothing is as it seems. And yet, we build our entire understanding of reality upon it. Every telescope, every photograph, every thought about the cosmos begins with the assumption that light tells the truth. But it doesn't. It tells its truth, one written by gravity. The beauty of that realization is that illusion and truth aren't opposites here. They're collaborators. Without that bending, we wouldn't see half the universe at all. Gravitational lensing lets us glimpse galaxies billions of light years away, magnified by the very distortions that mislead us. The universe tricks us, but in doing so, it also reveals itself. There's a quiet philosophical lesson in that. We often think of knowledge as removing distortion, of seeing things as they are. But in the cosmos, distortion is what allows us to see anything at all. Every curved beam of light, every delayed photon, every lensing arc is part of the universe's way of expressing itself. Not perfectly, but beautifully. Causality, too, becomes elastic. Light's finite speed and twisted path mean that every image of the universe is time-shifted. What we perceive as now is really a vast mosaic of thens, assembled from different distances and ages. You and I, in this moment, are surrounded not by the present, but by a museum of ancient light. It's as if the cosmos can't resist curating its own retrospective, and still we gaze at it, confident, curious, humbled, and call it reality. Perhaps that's the joke. In the greatest optical illusion ever made, the universe is both artist and audience. It bends its own light into forms that intelligent beings one day learn to interpret, even as they remain trapped within the same illusion. So the next time you look up and see a star twinkling, remember, it's not where it seems. You're looking through layers of distortion, across oceans of time, through gravity's glass. And somehow, through all that bending and delay, that photon has found you. In that moment, you and the cosmos are connected by one long, curved thread of light, a reminder that even in a universe of illusions, the beauty is real. The story of gravitational lensing is, in the end, a story about light's patience. For billions of years, photons have been crossing a universe that never sits still, expanding, stretching, reshaping itself with every moment. Each beam of light that reaches us has been bent by gravity, reddened by expansion, delayed by distance, and yet it arrives. It finds us. When we talk about the expansion of the universe, we often imagine galaxies flying apart through empty space. But in truth, space itself is what expands. The distances between galaxies stretch not because they are moving through the cosmos, but because the cosmos itself is swelling between them. Every second, the fabric of space-time stretches just a little more, like an ocean tide that never stops rising. And light, that tireless traveler, must ride those waves. As the universe expands, the wavelengths of light expand with it. They lengthen, shifting from blue to red, from visible to invisible. A photon, born in the ultraviolet blaze of an early star, may reach us as a faint microwave whisper. In that stretching, we can read time itself, the measure of how far and how long light has traveled. It's as if every photon carries a record of the universe's breath. Gravitational lensing gives us a way to trace that expansion, to measure how space curves and grows. When light from a distant galaxy is bent around a cluster, The amount of distortion depends not only on mass, but on the distances involved, from the observer to the lens, from the lens to the source, and through the fabric of expanding space in between. By comparing those patterns across billions of light-years, astronomers can calculate how fast the universe has been stretching, a cosmic ruler woven entirely from light and gravity. The results reveal something humbling. The expansion is accelerating. Galaxies aren't just drifting apart, they're racing away faster and faster, pushed by something we call dark energy. We don't know what it is, perhaps a property of space-time itself, a pressure that counteracts gravity. But we can see its fingerprints in lensing data, in how distant galaxies appear slightly more stretched than they should be. Even now, light is telling us that the universe is speeding up its own escape. And yet, in this motion, there's a strange constancy. Light keeps going. No matter how far it travels, no matter how much it bends or fades, it continues, steady, silent, enduring. Every night, sky is filled with photons that began their journey when the first galaxies were still forming. They've spent billions of years dodging gravity wells, threading through dark matter, passing near superclusters whose existence they couldn't have anticipated, and still they arrive here, on this tiny planet, to fall gently upon our eyes. It's an almost impossible thought, that your vision of the cosmos is made of light older than life itself, that when you gaze into the Milky Way, you're seeing a composite of billions of ancient messages, each one a survivor of collisions, expansions, and the endless warping of space-time. You are quite literally seeing the past bent into the present. Lensing reminds us that the universe doesn't simply exist, it performs. It choreographs the dance of light and gravity so that we, fleeting observers, can glimpse something eternal. Every arc in a deep-field image, every ghostly ring around a galaxy, every faint flicker magnified through a cosmic cluster, all of it is part of the same grand story, photons making their way through an expanding stage, carrying with them the memory of everything that ever was. And though the universe keeps stretching, those threads of light continue to reach us, connecting the most distant past to this single, fragile now. It's as if the cosmos refuses to let its story fade, as if it wants to be seen, even if what we see is distorted, delayed, and bent beyond recognition. So tonight, as the world quiets and the stars begin to shimmer, remember that the light touching you has been on its way since before the Earth was born. Bent, stretched, and slowed by all the gravity between, it still found its path. Across the vastness of time and the curvature of space, it has reached the one place where it could be seen, understood, and cherished. That place is here. That moment is now. And that light, ancient, weary, beautiful, is saying only this: the universe remembers. Thank you for listening, and good night.